Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To your seat. Sid has been working on coding distribution for quite some time. He's playing that in the summer here the work with me and Pablo on some coding distribution for media streaming. Today he will present some work he's been doing back at New York University. Now. And Sid will talk about the system that they have developed for scaling file servers called Shark. And system that
NSDI.
So if you have any questions during the talk,
Thanks, Christos, and good afternoon, everyone. Today I'll be talking about Shark, a novel scheme to scale file servers using cooperative caching. This joint work with Michael Friedman and David Maziris. Consider this scenario, like many of the computer applications these days could be conveniently structured as distributed systems. In this scenario, if you want to, let's say you want to test a new application on 100 nodes. One of the problems you're going to face is that you need to push this software to all the nodes and collect the results. One approach that you could take is that you could distribute all the software from a central server using tools like rsync, Unison, or SCP. The problem with this approach is that the server is going to quickly saturate its network uplink, delivering unacceptable performance. And in the process, this causes the operation to take a long time to finish. Also, this approach wastes bandwidth across bottleneck links as the one shown between network A and network B. Another approach that you could take is to use file distribution mechanisms like BitTorrent or Bullet. In these systems, the clients fetch data from each other, and hence they offload the burden on the server. But one potential problem with such systems could be that a client could be downloading from another client which is halfway across the world. But a bigger problem with this approach of copying files is that the users have to decide a priori what they're going to ship. If they ship too much, they're going to waste bandwidth, and the operation is going to take a long time to finish. If they ship too little, they'll have to go through the hassle of working in a very poor environment, devoid of like debugging tools. And I'm sure like anyone who has worked with Planet Lab would have experienced this at one point of time or the other. And like in distributed test beds like we have on Planet Lab, the ideal environments usually tend to consume a lot of disk space. And users are often unwilling to clean up these old files because of the pain involved in redistribution. So what we need is a low-cost solution for redistributing, for refetching new files. Also, whenever you want to like ship the software from a central server to all these remote nodes, you run into this problem of manual management of different versions of the same software. It would be great if we can create an illusion of having the entire development environment along with all the debug tools that we'll ever require present on the remote nodes. But these programs should be fetched only when they're actually accessed and are actually used. But this is exactly the interface that you get with network file systems like NFS, AFS, or SFS. We know how to deploy these systems, we know how to administer these systems, and the accountability mechanisms are very simple and are very well understood. So in order to see, but the big problem with network file systems right now is scalability. In order to see like how the performance would be, we took a traditional network file system SFS, and we tried to distribute a 40 megabyte package to 100 nodes on a local LAN. We see in this graph here, like I present the time that it takes for the operation to finish, that is to fetch this 40 megabyte package across 100 different nodes. And we see that this operation is quite slow, taking about 775 seconds or around 12 minutes. What I'm going to present to you today is something that does this an order of magnitude times better. So we would like to be able to finish this operation in like 90 seconds or so, which is 1.5 minutes. Of course, recent peer-to-peer file systems have produced, like Pond and Ivy, have shown scalability of this order. But unfortunately, they have like non-standard administrative models, and the file system semantics are also tend to be radically different. For example, in Ivy. And also, as these systems haven't been widely deployed yet, they couldn't be readily used and are not readily available. So a goal for Shark has been to retain this convenience of central servers and also like provide the scalability of these new peer-to-peer file systems. So let's get to designing this new file system. Let me emphasize at this point that Shark works with a central server model, and we have a central server as shown. We then add a large client-side cache a la AFS, and this scales the system by avoiding redundant data transfers. And we use leases in order to ensure cache consistency, and this works exactly like in NFS or AFS. But with multiple clients, the bandwidth concerns recur again, and we need to address this problem. In Shark, we solve this problem using cooperative caching. Essentially, the idea is that the clients fetch data from each other, thereby offloading the burden on the server. To this end, the Shark clients maintain a distributed index. And whenever a client wants to fetch a file, it does so from multiple other clients in parallel. So the unit of data at which a client fetches from another client is an LBFS style chunk, which is a variable size block. We pick these LBFS style chunks as opposed to fixed size blocks because chunks have better semantic properties. They exploit these commonalities across the files in a file system, and also these chunks are preserved across different versions of the same file. And finally, whenever Shark demonstrates locality awareness. For example, when a client could download the same piece of data from multiple clients, it does so preferentially from the one which is nearby to it. Another cool feature of Shark is what we term cross-file system sharing. Essentially, the idea is that all the clients would form a global cooperative cache irrespective of the origin servers to which the clients contact. So let's say there are two groups of clients, one group accessing server A and another group accessing server B. And let's say these client groups happen to share a large amount of software. Then what we want is that this client should be forming a global cache and pool together the resources of both of these client groups. What is a very good, like this. What is a very good application for this? Well, Linux distribution with live CDs. With a live CD, you can run an entire operating system without ever touching the hard disk. But like the number of programs that you can fit on a CD is limited by its capacity, unfortunately, while you want to access a large collection of software. One simple thing you could do is set up a server with all these programs. But like people do not do it these days because the server won't be scalable in that case when many people hit the server. So in this case, let's say there is a Knoppix server and there is a Slacks distribution, both of which set independent servers, and the clients want to fetch these all these programs. And clearly, there is going to be a large amount of overlap because all of these are Linux distributions. A large amount of software is shared between them. What we would want is that these Knoppix and Slacks users should be able to find each other and form a global cache, thereby relieving both the Slacks as well as the Knoppix servers. Let me now give you a roadmap of how cooperative caching works in Shark. In the first phase, the client fetches metadata from the server, and in the second phase, it uses this metadata in order to look up clients which are caching the chunks that it needs. It then connects to multiple such clients and downloads these chunks in parallel, and then finally, it verifies the integrity of the chunks that it has downloaded. Note that we envisage Shark to work in the wide area, and hence like we assume that the clients are mutually distrustful, and hence we need to check the integrity of fetch chunks. Okay, so is that clear up until now? Any questions? Yeah. Uh-huh. The clients do not
know which file they want to get.
Right.
Right?
Uh-huh.
But in the model you're describing here, the clients know which file they want to get.
Right, that's correct.
So how is it different?
So, one potential problem with BitTorrent is, as I mentioned, that like a client could be downloading from far away from the could be downloading from another client which is very far away, right? So like here, like we want to do it in a locality aware manner. Yeah, so that is one difference. And another difference is that like whenever we find some like, and second thing, like we provide a file system interface, whereas BitTorrent is like you'll have to manually ship files. Like, I mean, you need to tar up the files that you want a priori. You need to decide that a priori, and then you need to ship the tarball or something, right?
But in your model, the client says, I want file X, right? And then he goes to the server, gets the metadata.
Right. So let's consider.
It's the same, isn't it? He has to decide which file.
No, but it is transparent, right? Like it's like a file system. You say cd/shark/file, and like it happens in the background. Whereas with BitTorrent, you need to like set up a server with like that particular file. And let's say like you're testing some software, okay? You distribute the tarball to all the remote nodes. And then like now you see, okay, I want this particular debug tool. It's not, you haven't distributed it a priori. So you need to set this up again, right? Whereas like with Shark, you just access it and then like it either fetches it from the server if it is the first client, or it fetches it from the other clients. Okay. So, yeah. Right. Yeah, like, okay, we are assuming that latency is a first order approximation for like bandwidth, which might not be true in most of the cases, but like, yeah. Right, something like that. At least in the homogeneous kind of environments that we work in, like let's say on Planet Lab, that is definitely the case. For example, yeah. Okay, any more questions? Yeah.
The mental model I should be having is this work benefit combination of ODFS and BitTorrent. So it's like ODFS, but it has a cooperative-caching.
Right. So LBFS is not really like.
Because you're getting the file system interfaces doing the whole chunking, variable size.
Right. Right. So the reason we use these chunks is that they preserve the commonalities. That is the only use we have for the chunks. Yeah. Yeah. Yes. You had a question? Okay. Okay. So shall I go on? Okay. Yeah, you can write these files as well.
So any client might be writing any file.
Right. So for example, like after you performed an experiment, like if you want to write back the results, the remote client just writes it to the file system and they're automatically reflected on the server. Yeah. So it's NFS style leases. You have leases for 10 minutes or whatever, and then like, what? Oh, okay. So NFS v3, I'm not sure like comes with leases straightforwardly, but I think there is functionality of leases that you can add in. No. So we implement leases on top of. So essentially, like when I come to the implementation, I'll describe like we work with SF in the SFS framework. So the Shark client daemon is actually implemented as a user level server. So whatever happens is done at this user level, and hence like we implement leases at that point. Yeah. Okay. So getting into the details, in the very first step, the client gets the metadata from the server by sending a get token RPC, indicating the file that is interested in with the file handle. The server then sends back the metadata, which consists of these chunk tokens. So intuitively, what is this chunk token? The possession of this token implies permissions from the server to read this particular data, particular piece of chunk, particular chunk. Hence, because of this property, tokens are a shared secret between authorized clients, clearly. So how do we obtain this chunk token? We essentially hash the data with a collision-resistant hash function, like say SHA-1256. And then like these tokens could be used because of this property that H is a collision-resistant hash function. It could be used to check the integrity of the data that you have fetched. All right. So 3 concepts here, like possession of a token by a client indicates that it's authorized by the server to read that particular chunk. And then like because of this reason, between authorized clients, it forms a shared secret. And this token could also be used in order to check the integrity of the data that you finally fetch. All right. Yeah, so because the way in which you obtain this chunk token, you use a collision resistant hash function. So like after you do, so because of that property, like you can use it for verifying the integrity. Okay, now that you have fetched the metadata from the server, you need to discover the clients which have this particular chunks cached. For every chunk B, you have the client generates an indexing key, which is used to look up the particular clients which have this chunk cached. Note that we cannot use the chunk token itself as the indexing key because the chunk token is a secret, and it's shared between these authorized clients alone. You would not want an eavesdropper to track your lookups and find the chunk tokens, right? So the way we generate this indexing key is by just marking the chunk token along with a symbol which I indicate as indexing key here. So Shark achieves locality awareness because all the clients in Shark form an overlay which is organized as clusters based on latency. Hence, the indexing infrastructure returns you sources for certain chunks which are in the same cluster as the client if they exist. Otherwise, it falls back onto other clusters. Here, like chunks are usually transferred from nearby clients. Hence, this is the reason why like chunks are transferred from nearby clients. Okay, so now you have fetched the metadata, discovered some clients which have the chunk, and now you download the chunk. There are a bunch of security issues which I'll address later. And like once you download the chunk, you yourself are now a source for that particular chunk. And hence you register in the indexing infrastructure by using a simple put operation. Note that after a client downloads a chunk, it reuses the connection that it already has to a source to fetch more chunks. Essentially, they do a simple form of reconciliation of the chunks that they have. All right? You have a question? No, okay. Okay, so returning back to the security issues. How does client authentication takes place? How does the client authentication take place? It is exactly similar to like what happens in an FSA. Like you still have the notion of UIDs, GIDs, the notion of users and groups like in Unix still hold. But like the new challenge now is that how does a client know when to send a chunk to a client? It should have some form of like authorization. It should be able to check the client's authorization. And in this context, the chunk token allows a client to identify authorized clients. How do we do that? Let's see. So let me now identify what should be some of the properties of the security protocol involved in Shark. First of all, a client should be able to check the integrity of the chunk. A client should be able to check the integrity of the chunk that it has fetched. And then secondly, a client should not send chunks to other unauthorized clients. And finally, an eavesdropper should not be able to track the data that is being sent over the network. Coming to the details of the protocol, let's say a receiver client wants to fetch a chunk which is shown in green from a source client. In the first phase, they exchange random nonces in order to ensure freshness for the session. In the second phase, the receiver sends an indexing key indicating the chunk it is interested in, along with an authenticator. This authenticator proves to the source like that the receiver client indeed has the chunk token. Because of the property that the authenticator is derived from the chunk token using a MAC. All right. And finally, the source client sends the data encrypted with a key K, which again is derived from the chunk token to the receiver client. So what were the properties we wanted from this security protocol? We said like a client can check we said that we want the client to be able to check the integrity of a fetch chunk. So the client here essentially downloads the chunk and then hashes it and then verifies that it is equal to the chunk token that it has got from the server. Secondly, we said that the source should not send chunks to unauthorized clients. We note that malicious clients would not be able to send the correct authenticator to the source, and hence such clients are like forbidden. And finally, we said like the eavesdropper shouldn't be able to get access to the chunk contents, and this is ensured because like all the communication is encrypted with a key K. So K is like you essentially derive it from the chunk token using a MAC with a special symbol encryption shown as E, and hence like this is a shared secret between like two authorized clients. One sec. What is it? Message authentication code. So yeah, maybe we can discuss offline like what the properties of it would be. It's like fairly standard. So was that clear by the way? Okay, good. So note that the security protocol, as I have described here, has certain limitations. For example, what could happen is that an eavesdropper can track the lookup of the lookups that are being made by the clients. Like for example, like the client would be sending bunches of indexing keys into the network. The client can just like track these lookups, and then like if the eavesdropper has some idea about like what the client is downloading, let's say the client is downloading Microsoft Windows or something, then like the eavesdropper himself hashes the data and verifies what the indexing key is, and knows that like this particular client is like downloading Microsoft Windows. This is like this is not the best privacy that we could get. Like if we want more privacy, like we have a minor variant of this protocol which is described in the paper, but that solution would actually sacrifice the cross-file system sharing that I have previously talked about. So this is the trade-off: better privacy versus cross-file system sharing. Also note that since all the client-to-client communication is based on this chunk token acting as a symmetric key, no forward secrecy is guaranteed by these protocols. And now coming to the details of the implementation, the SHA client daemon is actually structured as a NFS loopback server. So whenever an application accesses a SHA file system, the NFS client in the kernel forwards the system call to the SHA client daemon, which fields this request. The SHA client daemon then forwards the request either to a SHA server or to other SHA clients. Note that the core daemon present in each of these clients forms a node in the indexing infrastructure that I have talked about. Coming to the evaluation of SHA, we wanted to answer the following questions. How does SHA compare with more traditional file systems like SFS and NFS? And how scalable is the server? And how fair is SHA across different clients? And also, like when you want to fetch a whole file, like you need to fetch these chunks in a certain order. Like, and we wanted to see like which order would do better, random or sequential. And also, we want to characterize the benefits of set reconciliation. So to this end, like we performed an experiment on Emilab, which is essentially a cluster of local nodes at Utah. We did our experiments on 100 nodes. In this experiment, we wanted to distribute a 40 megabyte package from a central server to all these 100 nodes. And in this graph on the y-axis, we show the percentage of nodes that have finished this operation. And since like the number of nodes happens to be 100 here, like, and the percentage is for 100, like it indicates the number of nodes too that have finished in a particular at a particular y coordinate. So we see that like Shark does 9 times better than SFS and like 4 times better than NFS. Note that NFS already has this unfair advantage that it actually runs in the kernel and also doesn't involve any cryptographic overhead because like it's all the protocols are insecure. A curious observation here is that like SFS seems much less fair than the other two systems. This is because this SFS servers uses TCP as the communication transport, and hence like it drives some of the connections into backoff because of congestion. And then like because of this, the clients finish at a more gradual pace, and hence the difference in the curves. We performed the same experiment on in the wide area in order to like validate the results, and we did this experiment on 185 nodes on Planet Lab. Here again, the graph on the y-axis shows the percentage of nodes that have finished this operation across time. We see that while Shark finishes the operation in around 7 minutes, SFS was taking 39 minutes for the same operation to finish. And unfortunately, we couldn't test NFS in this scenario because it was triggering kernel panics in our server. So the big claim of Shark is the scalability, and we wanted to see how scalable the Shark server was. And here we see that while the Shark server pushed like 23 copies of the data, an equivalent of 23 copies of the data, SFS was pushing like 185 copies. In a sense, like Shark gives you an 8x improvement here. So we wanted to also make sure that Shark doesn't shift this burden from the server and put the load on other client. So we wanted to see like what was the amount of data that was served by various clients. And here we see that the maximum contribution of any client is an equivalent of 3.5 copies of the data with a minimum contribution of 0.75 and a median contribution of 1.5. Yeah. You mean like one particular client is being overloaded by many different clients or something like? So I do not see the argument. I mean like, let's say like you're saying like a client is there and then like it will face congestion and it will. Uh-huh. Yeah, maybe we should take this offline actually. Yeah, you had a question?
You mentioned earlier in the talk that when a client wants to block sends parallel requests. Maybe I missed it, but did you say that how many actual requests issued for the same block?
For the same block?
Yeah, it looked like earlier in the talk you were describing that when a client wants to request, it issues parallel requests.
Yeah, sorry. So maybe I should have made it clear. Like that is when fetching a whole file. Like for a chunk, it issues one request. Essentially, it looks up in the indexing infrastructure for the guys who are caching that, and then it picks the one like which has the like lowest latency kind of a thing.
Parallel requests is if you want to get a whole file.
Right, right. And like since we use like AFS style whole file caching, we actually like prefetch the whole file when a part of the file is accessed. Though we have some heuristics to like for commands like tail which access just the last part so as to make them fast. Yeah, but that's a side note.
Presumably, if the client doesn't respond,
Right. Yeah. Yeah. Essentially, like you parallel. Let's say like the indexing infrastructure returns you 5 nodes, which have this chunk. Then you simultaneously issue 5 parallel requests, and you pick the one which returns first, kind of a thing. Like right now, that is the scheme. You pick the one which returns first, like which responds first.
this is for pros to see which ones are closest to you, or this is for actually asking the data?
This is for actually asking the data.
So you are asking multiple clients for the same data?
So I issue like multiple probes to multiple clients that have been returned to me by the indexing infrastructure, and I just pick the one with the lowest latency, the one which responds to me first. So it's only one client that I fetch the data from. So the chunk is the minimum unit of data at which you fetch anything. Like there's no smaller unit than a chunk, and a chunk is approximately like 30K, you can say. So to give you a rough idea how it works. So when we wanted to fetch this whole file, we see that we have to fetch these chunks in some order. And 2 natural choices that we have considered here are random versus sequential. The reason we considered these 2 choices were like when multiple clients in the random strategy, when multiple clients fetch chunks, they usually like fetch independent chunks, and hence they diversify the cooperative cache. And thereby like more chunks will be available in the cooperative cache to fetch from. While sequential suffers from the drawback that only the client that downloads the most chunks alone adds to the cache, it could potentially result in better disk I/O scheduling. But we weren't hitting the bottleneck at least up until like this 200 nodes kind of a thing. So we verified our experiments again on EmuLab, and then we found that random was actually performing 35% better than sequential strategy when you want to fetch a whole file. And finally, we wanted to see the benefits of reconciliation. And in the same scenario, we found that reconciliation offers like 35% improvement. Whenever like a client starts to fetch chunks from another client, after it downloads that particular chunk, it will query for other chunks that it has that of interest. So like essentially they do a set reconciliation kind of a thing. Hey, I have these chunks, you have these chunks, so let's see what are of mutual interest to us. So essentially like here we send the indexing keys which identify that particular chunk. So each of the clients maintains a list of the indexing keys which it has in the cache, for the chunks it has in the cache. And so like I send the index, it's like a shortcut lookup essentially. One second. Tracker per key. No, tracker is for like finding other, like essentially it's a distributed tracker, you can say, like if you want it, if you want to view it like that, Yep. Yeah. So how does the server have knowledge to, like, I mean, the server has only partial knowledge, right? Like, how can it like, and anyway, we don't want to load the server, number one, and the server also doesn't have all the information that is required to schedule it properly, number two. Now, I do not see like, I mean, like, do you have a concrete thing in mind?
But you are paying random
Right. Mm-hmm.
but then everybody end up making the same chunk.
Right.
So one possibility seems like you could get around this by saying, give me this chunk. Take a chunk out of these slots because I need all the information.
Oh, right. So you're essentially saying like, I say, give any chunk kind of a thing, request. Yeah, that is something that we wanted to consider, but the reason we didn't do that was sequential wasn't hitting the bottleneck as of that point. So like we didn't test it at that point. But yeah, that's a good suggestion. Like, yep. So in conclusion, network file systems offer a very convenient and powerful interface for accessing remote storage. But unfortunately, current network file systems like NFS are not scalable. And this forces users to resort to inconvenient tools like rsync and so on. What SHA gives you is this convenient file system interface, while at the same time scaling to hundreds of clients. It does so by making an intelligent use of its locality-aware cooperative cache. And finally, SHA supports cross-file system sharing, enabling novel applications like Linux distribution. Thank you. Yeah. You mean like could it be used as a substitute for AFS? Yeah, like it's AFS plus something more, right? Essentially. Yeah, and like I'm not sure if AFS does security or something, but if security is a concern, then like this could be a drop-in replacement. That was actually one of the goals. This should be a drop-in replacement while at the same time being secure and better for read-heavy workloads. So that was the main goal. Okay. Right.
File systems maybe they're smaller files.
Mm-hmm.
The popularity of the file on the different computers is not as good. So you have to look for more realistic workloads, how an efficiently spent.
Right. So you're saying like if a file is of less than 1K size, why not fetch it from the server, and why do you want to fall back on the cooperative cache, those kinds of stuff? Right. Right, that's correct. So the hope is that like one thing we were actually gearing towards plant lab kind of scenarios where like this is exactly the need, where you want to distribute it. So that is one part of the answer. The second part is that like, I mean, when you go over a long period of time, hopefully like most of the things will be in the cooperative cache. Let's say like Linux distribution with live CDs, right? For that application, like hopefully you'll build up a cache like over a period of time. So it will be useful even in that case too. So yeah, these are the two kinds of scenarios where it would be useful. But if it's like, yeah, like I mean, clearly Shark wouldn't work if like all the clients were accessing totally different files and there was no overlap, right? If there is no overlap, like cooperative caching doesn't make sense at all, right? Yeah, in that case, like Shark won't perform. I mean, like it would perform no worse than like NFS, but it isn't particularly useful. Yeah, that's correct. Any more questions? Yeah. Sorry, could you speak up a bit loud?
What about faults?
Faults.
Yeah,
Okay.
If your client has you're getting just from
Uh-huh.
Right.
So let's say I'm now, so the client essentially has something like threads for each of the client. You can say like loosely threads. So like whenever I discover that a client has died, previously I mentioned that like the indexing infrastructure gives me like 5 nodes or something, right? So like I fall back onto another guy and download that chunk. So yeah, there are a whole bunch of like these failure scenarios which need to be addressed. Yeah, yeah. Okay, any more questions?